All right, hi everybody. Welcome to CS224 presentation number 1. I'm titling this screencast 5 Realities Part 1. In this video, I'm going to begin introducing some of the motivations for a class like this CS224 class, a systems class in general. Why do we want to know the kinds of things we're going to be studying in this course? So let's hop in. In terms of the overview for this presentation, I'm going to start with a course perspective, followed by a course theme. So beginning with perspective, why are we approaching this class the way we are? And then the idea of the theme being an overarching idea for you to keep in mind as we go through the class. Why is this important from a grand scale, from a high level? And to do that, again, I'm going to introduce then 5 realities or 5 motivations that give concrete examples of the kinds of things that we deal with in the real world, that situations in which you'd be benefited by having this information. Now, I'm not going to go through all 5 of these in this presentation. I'll get through the first 2, and we'll look at the last 3 in the next one. So, course perspective. Systems courses are not new. Computing system courses have been taught for many years. This course, however, takes an approach that is in some ways a little bit more modern from a programmer's perspective. So, where most computer systems courses are builder-centric, they're constructed in a way that reflects the kinds of things that someone who's actually going to build a computer would want and need to know. So for instance, when you talk about computer architecture, you're actually going to look at technologies that would be used to actually design and implement a computer architecture. And that's not something that most of us do. Operating systems, most of us won't actually build operating systems or even parts of them, and so forth. So you see kind of these other topics. And though each of these topics is very important to a programmer, they're important in a different way. The programmer needs to understand how these things work from the user's perspective and the ramifications of the decisions they make in the context of those particular systems. So, the operating system and the compiler and so forth. And those are 2 different camps. There are things that a programmer deals with on a regular basis and needs to understand very well that the implementer really doesn't need to deal with all the time. And so these are enough different that, again, these gentlemen from Carnegie Mellon actually decided to create a course from the programmer's perspective, which is more appropriate for many of you. So we're going to look at it from the programmer-centric point of view. And what we're going to try to do is show that by knowing more about the system and how it works, you can become more effective programmers. The way we're going to do this is show you how having this knowledge and understanding enables you to write programs that are more reliable, more efficient, and also put you in a situation where you can incorporate features into your programs that would otherwise be beyond you. The ability, for instance, to interact with the OS in a more powerful way for purposes of concurrency, signal handlers, and things like this. Okay. So we're going to cover things in this class that you're not going to see in other classes, but that will be useful in other classes and in other settings. It's the kind of stuff that may be taken for granted that in courses here at BYU, and in many situations will give you an edge over someone who doesn't have that kind of information. Now, the kinds of things that we will look at, you'll probably begin to see how, wow, this is the kind of stuff that a hacker would use to exploit a system, or a vulnerability in a system, rather. And it's absolutely true. However, I do want to point out that this course is not just for people who who want to be hackers, though you're going to get to do some things that are going to make you feel that way. The fact is that if you understand what a hacker does, then you can defeat the hacker and you can protect from them. This isn't the only reason for knowing these things, of course, but it is a useful one. And so, they like to say we bring out the hidden hacker in everyone. Well, at least for a little while. In terms of a theme, then, one of the ideas that I would really like for all of you to understand and internalize is this idea that abstraction is a double-edged sword. We use abstraction in computer science all the time. And one of the reasons that most people who use their computer don't know how it actually works is because of this thing called abstraction. It enables you to use a system without having intimate knowledge of it. And in most cases, that's very beneficial. We don't expect the average citizen, if you will, to understand everything about their computer, and we don't need them to in order to use it to complete the task that they are charged with. And so abstraction is a good thing. At the same time, we do need to have a certain subset of people who do understand what's going on under the hood, so to speak. Otherwise, we lose the ability to build the computers, and also we won't progress. Okay, these abstractions can limit us. So where most CS and CE courses emphasize abstraction in the form, for instance, of using abstract data types and asymptotic analysis. Asymptotic analysis, by the way, is where we look, for instance, at an algorithm and talk about its big O complexity, you know, how many operations are needed relative to the size of the problem we're trying to solve, and this kind of thing. And you'll recall that when we do that kind of analysis, we tend to ignore constants and only look at the largest terms that are involved. Such abstractions have limits, though, especially when things go wrong, right? And we see this in real life, right? You drive down the road in your car, and many of us have very little understanding of what's happening under the hood. That doesn't keep us from getting to point A to point B until something goes wrong. And it's at that moment that, you know, you see people popping the hood and there's this look of desperate confusion on their face because they have no idea what's literally happening under the hood. And so it's in those moments that the abstractions now are a hindrance. And if the abstraction has actually prevented someone from gaining understanding, and in the case of automobiles, that's usually the case. It's even worse in the case of programs. You know, most people, if something's going wrong on their computer, have no idea how to even begin diagnosing that. So this is where these abstractions have limits, for instance, is where there's a bug. And so then there comes this need to understand the details of the underlying implementations in order to address problems such as that. But that's not it. You know, in terms of getting more performance and so on, obviously you have no chance of doing so if you don't understand where the performance you're currently getting is coming from. So there are multiple useful outcomes to taking this course. We want to make you more effective programmers, helping you to find problems and defects in code, as well as being able to tune and improve the performance of such code. And this class will also then, of course, prepare you for later classes in CS and ECE. All right, so let's jump into some examples of things that we can think about and relate to, and maybe have even encountered, and how, and the fact that these are things that we're going to shed light on in this class. All right, so reality number one. Ints are not integers and floats are not reals. So it's a common mistake. I've witnessed it. I'm sure I'll continue to witness it, that incoming freshmen at any university start to associate ints with integers and with a set of integers specifically, and floats with the reals. Oh, I want to store a real number, I'm going to store it in a float. That's not exactly what's going on, and it's important to realize this. So to demonstrate that, here's a little cartoon from XKCD. Some of you are familiar with these cartoons. But here we've got an individual laying on a bed counting sheep, right? So each one gives out a baa as it goes over the fence, so you can add audio in your own mind, right? And you see this person counting, and apparently they're really having difficulty sleeping, because in the second frame they've gotten up to 1,306, 1,307. You see them kind of hugging their pillow there. And then in the third frame, something interesting happens. They're up to 32,767, and then suddenly it jumps to negative 32,768, and you see all the sheep piling back over the fence to the other side. and as the individual continues to count, now we see negative 32,767, negative 32,766. So they're working back up in the positive direction, and of course this poor soul has completely given up and now has their head under the pillow and is trying to hide from the sheep. What's happened here? Well, this is a little tongue-in-cheek, but it's actually reflecting something very real if this person's mind was a computer with a 16-bit int representation. So let's look a little closer at that. So, for example, in the real world, if you will, is x squared greater than or equal to 0? And we know that if we're talking about the set of integers, yes, x squared will always be greater than or equal to 0. And it turns out if you're working with floats on a computer, that will also be true. But in the case of the data type of an int, specifically in the C languages, that's not always the case. So here, if we look at 40,000 times 40,000, we will get 1.6 billion. So x squared was greater than or equal to 0. However, what happens if I multiply 50,000 by 50,000? Now the correct result should be about 2.5 billion. No, about. It should be precisely 2.5 billion. However, we've got question marks here because it turns out that if we're using a signed int representation and we have a 32-bit data type, that will not be a positive 2.5 billion. You'll actually end up with some negative value. Okay, and we're going to discover why that is. Understanding that reality and why that happens is very important. You'll notice, for instance, that in this case we're talking about a 32-bit value and we're dealing with very large numbers. You'll notice in the cartoon here we're looking at a 16-bit value and the problem arises around 32,700. Okay, so it's not just enough to know it'll happen. We need to know why it's happening so that we can understand where it will happen in our number system. All right, example 2. Here's a simple equation. We've got the quantity x plus y plus z, and we see that that's equal to x plus the quantity y plus z. Right? So we're looking at associativity here, and these two things should be equivalent. And it turns out if you're working with unsigned and signed ints, they will be. Okay, so associativity will hold. However, it turns out that if you're dealing with a float data type, something funny happens. So here we have the quantity 1 times 10 to the 20th plus negative 1 times 10 to the 20th. Okay, so those two should cancel each other out. Plus 3.14. So the result should be 3.14, and it turns out in this case that that is what we would expect to get. The first quantity inside of the parentheses will evaluate to 0, and then we'll add 3.14, and that will be our final result. However, if we were to move these parentheses and instead say that we want to add 1 times 10 to the 20th to the quantity negative 1 times 10 to the 20th plus 3.14, what will we get? Well, it turns out you won't, in many cases, get 3.14. And the reason has to do with this initial quantity. We have a limited amount of space within which to store 1 times 10 to the 20th. You can't store a number of that size as an int. You can represent it using a floating, a 32-bit float data type, but it comes at a cost. And it turns out that as the magnitude of a value gets larger, in order to store it in a limited space, we reduce the precision. And so this value, negative 1 times 10 to the 20th, has a very large magnitude. And so it turns out that 3.14, which is relatively tiny compared to, in terms of magnitude, compared to this negative 1 times 10 to the 20th. And so what happens is it's essentially discarded. You could think of it kind of like a truncation error. And so instead of having the value 1 times 10 to the 20th plus 3.14, you actually are going to end up with something more like negative 1 times 10 to the 20th. Okay, so then when that gets added to 1 times 10, that negative value gets added to its positive version, then you end up with 0. Right, now this is going to be somewhat system dependent, and so that's part of why we've got the question marks here, but the key here is that associativity is not holding in this case because of the way the data types are being handled. All right, so this is important to understand. And so when we're doing computer arithmetic in general, we need to know that we can't assume all of the usual mathematical properties. And that has to do with the kinds of of representations over numbers, and in particular the fact that they're finite. We're working with a subset of these types of numbers. Ultimately, we will see that integer operations tend to satisfy the ring properties such as commutativity, associativity, distributivity, and so forth. Floating point operations, they satisfy ordering properties. So monotonicity, I said it, all right, and the values of signs. And we saw that these two situations in the previous examples. So strengths and weaknesses to both representations. That's in particular important for people who think that they can just store all the reals in floats, because they start believing they can solve all their problems just by using floats, because they can store any size number that they want, and so they don't want to use ints because they think that it's more limited. Hopefully this little demonstration has showed you that that's not the case, that in reality sometimes you want to use an int and sometimes you want to use a float. In order to make that decision, you need to understand the underlying mechanisms of these two data types. Okay, so quick observation, I already kind of said this, but again, we need to know which abstractions we're using and how they will impact, how they will affect the performance of our system in a particular context. And such things are very critical for people who are doing things like writing compilers, as well as any other kind of serious application programmer. If you're working on a missile system, for instance, or a safety system on a jet or a medical device, these are not situations in which you can afford the math to go wrong. People's lives are in danger. And so, especially in those kinds of environments, you need to have developers, you need to have software engineers who understand how the computer works and the implications of the data types that are being used. All right. Reality 2, assembly isn't just for compilers. Now, we get it. You're not a compiler. You don't want to be. That piece of software is much better and more patient than you when it comes to writing machine code. In fact, when it comes to writing assembly code, which is not exactly the same as machine code. So we understand that. Let's get that out there. We're not imagining you're going to sit and write assembly code. However, understanding how assembly works and understanding the language that's actually available there and being worked with by your compiler is very useful when we're trying to do things like understand the presence of bugs. The abstractions that we use in high-level languages don't capture some of the edge cases in terms of behavior at the actual assembly level implementations of our programs. And so that's one reason we want to understand this. When it comes to the performance of our programs, understanding the kinds of optimizations the compiler can and cannot do. Well, these things are being done, some of these things are being done at the level of assembly language. And also understanding the inefficiency of our programs and why they're not working as well as we would think. Finally, the issue of system software. If you want to do something like write a compiler, then you are going to need to understand assembly, and you're going to be working with that intimately if you're working with the back end of that compiler. In addition, operating systems, they have to manage process state, and that very generally needs to be done at a lower level than high-level languages allow us to interact with the system. Okay, so there are several situations in which you are going to need to understand assembly and how it behaves. Not finally, I thought I was done there, but also the issue of creating and fighting things like malware. x86 is the language of choice for someone writing viruses or such harmful types of software. We don't want you writing that kind of stuff, but we do want you writing code that is safe and that is resistant to the kinds of exploitations that those individuals take advantage of. So if you understand the tools they use, then you can understand how to defend against them. Okay? All right, so I'm going to stop there with this presentation. In the next part of this presentation, I will discuss the last three, or I should say the next three realities that inform this course and the kinds of things we're going to learn. But let's take a break for now, and I'll see you next time.